So good afternoon everyone and welcome to this second live session of this course on Introduction to Polymer Physics. So after this is a final live session that we are going to have, and after that next month you'll be having your examination. So if you have any questions, any queries or any doubts about the course in general or even about any assignments, then you can discuss that in this current session. So if someone has any questions, they can type in the text box and then I'll try to respond. So since at the moment there are no questions, I'll just briefly review uh, the material that was covered after the first live session. And then after that, again, if you have any questions, I can try to answer those. Yeah, so the first live session was carried out or conducted after the first 4 weeks of this course. After that, in week 5, the focus was on the study of branched polymers and network polymers and the phenomena of gelation. So in branched polymers, we specifically focused on hyper branched polymers of a certain type. And after that, we discussed dendrimers, which are also a type of highly branched polymers, but there's a certain order to the way in which branching takes place there. So these were the specific cases that we discussed under branched polymers, and then we moved on to network polymers, where we studied the concept of gelation, briefly discussed the Fleury-Stockmeyer theory of gelation, uh, and towards the end of this week we uh, also talked about the Fleury-Renner theory of swelling. So when a solvent is added to a network polymer, instead of the polymer getting dissolved in the solvent, you actually have swelling of the polymer. So that was discussed in the Fleury-Renner theory and the corresponding equation which describes this swelling behavior. That was also discussed in this towards the end of this week, which was week 5. So we can, yeah, so here what I'll do is just briefly discuss an example problem. A problem like that might have appeared in one of the assignments that you got. So I'll briefly just talk about an example problem involving dendrimers. So the question here is that we have a dendrimer which is formed by the polymerization of a certain type of monomers, which are AR BF minus 1 plus BN type monomers, and the values of F and B, F being the functionality of that functional group B in ARB type monomer, that is given, and the value of N is also given. And the question is to find the ratio of the number of monomers in the 5th generation to the number of monomers in all the generations up to the 4th generation in this dendrimer. So to solve problems like this, the expressions for finding out the number of monomers in any particular generation, that was discussed in class. So that we already have here, and we substitute since our generation is 5, so that's why this 5 is used. This corresponds to the generation number. NNF are 4, so we substitute those and we get 324 as total number of monomers in the 5th generation only. And if we count the number of monomers up to the 4th generation, the general expression for that again was discussed, where again this G is the generation number, which is 4 in this case, So up to 4th generation, if we substitute the values of n and f as well, we get the values 161. And after this, if we want to find out the ratio, that is 324 by 161, which comes out to be very close to 2. So while discussing this topic, we had covered this fact that this ratio usually is close to 2, especially if we the higher the number of generations we are looking at, the closer this value, this ratio will be to 2. Okay, so this is one kind of example problem on this topic of dendrimers. And in the next week, that was week 6, we discussed amorphous polymers as well as crystalline polymers. So in amorphous polymers, we specifically focus on this very important phenomenon called the glass transition, which marks a transition from a hard and glassy rigid state of the polymer to a soft rubbery state. So the temperature at which this transition takes place is called glass transition for a polymer, and this is observed only for amorphous polymers. We briefly talked about the thermodynamics of glass transition here, free volume theory of glass transition, and also different factors which affect the glass transition temperature of an amorphous polymer. And then for crystalline polymers, we talked about the different kinds of crystal structure that we can have, and the concept of this degree of crystallinity. So polymer samples in general can be semi-crystalline, which have both crystalline and amorphous fractions. So this degree of crystallinity is a measure of the amount of crystalline fraction that you have in the polymer sample. We talked about kinetics of crystallization, particularly the Abrami equation describing its kinetics, and finally the factors which affect the melting temperature. Excuse me. And we again, towards the end of this week, we briefly touched upon this mechanical properties that is stressed in relationship for for polymers. So here, with regards to this week, let's just briefly discuss one sample problem, which is again, which may be similar to something that you may have solved in one of your assignments. So we have here two homopolymers having glass transition temperatures 320 and 400 Kelvin, and a miscible blend of these polymers is formed, and that has a glass transition temperature 350 Kelvin. And it's said that the Fox equation can be used to for the glass transition temperature calculation for the blend, and the question is to find out the weight fraction of homopolymer A in the blend. So the Fox equation is this, that was discussed during this course. The weight fraction of A is WA, that of B is WB, and since these are the only two components present in the blend, their sum would be 1. So WB we can write as 1 minus WA, and then the values of the glass transition temperatures we can just substitute here. So we get these 350, 320 and 400 as the respective values. Then all we need is to rearrange the terms in the equation to solve for WA. And it's usually better if you do not calculate the individual fractions initially. So instead of calculating what 1 over 350 is or what 1 over 320 is, we can just work with these numbers and simplify the equation further by moving the terms around. So, and finally we can solve for this WA. So if you do that, then WA comes out to 0.57. The reason why it's preferable to keep these fractions in that form till the very end of the calculation is that will basically prevent any rounding of errors from happening in the intermediate part of the calculations. Okay. So that was week 6, and then in week 7 we focused on viscoelasticity of polymers, which is a very important property of polymers and polymeric solutions, and also rubber elasticity, which is specific to which is something that is specifically exhibited by elastomers. So when talking on viscoelasticity, we consider two different mechanical models, the Maxwell model and the Kelvin-White model, and we discussed how these models can be used to study the creep and stress relaxation behavior of polymers. Then we also touched upon some other topics uh, in under viscoelasticity, which was the concept of creep compliance stress relaxation modulus and the Boltzmann superposition principle, and finally the dynamic mechanical analysis, where you have sinusoidal variation of the applied stress or strain and the corresponding responses studied. So, and we also very briefly talked about polymer rheology, which itself is a very rich and diverse field. So we just briefly noted that polymers and polymer melts and solutions exhibit strongly non-Newtonian behavior. In many cases, the behavior is shear thinning, where increase in shear rate leads to a reduction in viscosity. And we also talked about the dependence of rheological behavior of polymers on the temperature and the molar mass of polymers. And finally, we discussed rubber elasticity, which is specific to elastomeric polymers. We discussed thermodynamics of rubber elasticity. One simple model which to describe rubber elasticity, which is the affine network model, and a phenomenological equation for describing rubber elasticity, which is the Mooney-Rivlin equation. So let's just quickly look at again one sample problem here. So the question is that we have and this question is on rubber elasticity. So we have a certain number of network strands per unit volume in an elastomer. The value is given as 500 mole per meter cube. And it's given that the affine network model applies. The question is to find out the work per unit volume that is required to stretch this elastomer to twice its original length at a certain given temperature, which is 25 degrees Celsius. So here, since the affine network model applies, we can directly use the expression for this affine network model that we studied during the course for the work required. And if the deformation is uniaxial and we assume no change in the volume of the elastomer, then the work done per unit volume for this affine network model is given by this expression, where this n is the number of network strands per unit volume, small n. Kb is the Boltzmann constant, T is the absolute temperature, and this small n by V then would be the number of network strands per, small n is just the number of network strands, and this V is volume. So n by V is the number of network strands per unit volume, which is given as 500. So here n by V is given, temperature is given 25 degrees Celsius, we can convert it to Kelvin. Lambda is 2 in this case, so it's deformed to twice its original length. So lambda is equal to 2. And this n by V that we have here given as 500, that is in mole per meter cube. So we will convert it to number of molecules per meter cube from moles. So 1 mole is 6.022 into 10 to the 23. So we multiply 500 by that, and this is the number of the actual number of network strands per unit volume. So we'll use that. Temperature is this, lambda is 2, and Kb, the Boltzmann constant, is the ratio of the universal gas constant and the Avogadro number. So that is a very standard constant, and its value is 1.38 into 10 minus 23 joule per Kelvin. So we have all these in this information. We can substitute everything in this equation and find our work per unit volume required for this extension or deformation. So this is the equation, and if we substitute everything here, then all the numbers, once we substitute and simplify, the value of work per unit volume that we get is close to 1.25 or 24 megajoules per meter cube. So that's the that is the solution to this problem, and here it was just a direct application of the equation that we have uh, studied during this course. Uh, Only thing was to understand the values, the different parameters in this equation, and what those parameters correspond to in terms of the values given in the problem. So so this was week 7, and then in the last week, that was week 8, we focused on polymer dynamics. So we uh, we only touched upon the introductory topics in polymer dynamics. Polymer dynamics itself is a uh, quite advanced topic, and we just focused on the simpler introductory aspects of polymer dynamics. So in terms of unentangled polymer dynamics, we studied the Rouse and Zim model. Uh, the for entangled polymer dynamics, we studied what are entanglements in polymer melts, and then the tube model, and finally this concept of reptation. So in polymer dynamics, all these topics were studied again at an introductory level, and here what we'll do is just briefly look at one example problem, which is based on the Zim model. So when we studied polymer dynamics of different topics, Rouse model we saw was applicable to short chain polymer melts, where you do not have entanglement in the polymer chain, but there are no significant hydrodynamic interactions. So for that, Rouse model is something that can be applied. Zim model is something which is applicable for polymer solutions because it takes into account hydrodynamic interactions. And finally, the reptation, the tube model and the uh, reptation model, those are applicable for dynamics of entangled polymers, where the polymer chains are long enough so that they can get entangled with each other, and the motion of a chain is strongly affected by the presence of all the other chains in its vicinity. So here we'll just briefly look at one example problem which is based on a Zim model. So in this problem we have a dilute polymer solution which can be described by the Zim model, and the polymer is expressed is represented as consisting of 100 beads connected by strings. So it's a bead string model of the polymer having 100 beads, and the root mean square size of these interconnections between the beads is 5 angstrom. At the theta temperature of the polymer, which is given as the polymer solution, which is given as 35 degrees, the viscosity of the solvent is also given here. So the question has 3 parts. One is to calculate the friction coefficient, then the diffusion coefficient at that temperature, and finally the Zim time. So this the information that is given to us, we can first list that information down. Solvent viscosity at the given temperature is of 35 degrees is given as 5 into 10 minus 4 pascal second. The number n of these uh, we can say Kun monomers, let's say, which are the springs that connect these beads, that's given. So we have 100 beads and the corresponding interconnecting springs are there. So the number of that beads is 100. The size of our Kun monomer uh, is, which represents, let's say, 1 unit of the one unit in the entire polymeric chain. That size is 5 angstrom, which is the size that's given here. So that we'll express in meters, the SI unit, and temperature in Kelvin. And then at the theta temperature, it's known that the size of the polymer chain is given by the Kun length times square root of the number of Kun monomers. So this comes from the fact that at a theta temperature, the polymer chain behaves like an ideal chain, So uh, so we have this expression here, and we substitute the values. The size, an estimate for the polymer chain size is obtained as 5 nanometers. And the friction coefficient of the chain is in this ZIM model is approximately given by the solvent viscosity and the size of the polymer chain, their product, so which comes out to be this. So that's the friction coefficient that we get here. And yeah. And the second part was the diffusion coefficient. For that, again, the expression was derived in the not really derived but stated in the during the course. So this is the expression for diffusion coefficient in ZIM model, and approximately this factor here is 0.196. So we have that Kb is known, that's a Boltzmann constant, temperature is known, and this solvent viscosity times the polymer chain size that we calculated in the previous slide to be the friction coefficient. So that's also already calculated. So after simplifying, we get this 3.34 into 10 to the minus 10 as meter square per second as a chain diffusion coefficient for this ZIM model. And finally, the last part is the ZIM time, which again the expression for this ZIM time was again discussed in during the course, and that's this. So everything that appears on the right hand side, these are known to us. R we already calculated in the previous slide as B times square root of n, because we are at the theta temperature, and we substitute everything, and this ratio, this factor 1 over 2 times square root of 3 pi, that is approximately 0.163. So we simplify, and finally we get around 2.4 into minus 9 seconds. So for questions or problems of this kind, the expressions are all available, so we can use the expressions. Only thing is that in some cases we'll need to calculate the size of the polymer, so depending on the information given, that has to be done. And after that you can just substitute the appropriate quantities in the expressions that we have to obtain the final results. And this was for the ZIM model, but we can have similar problems for Rouse model, or even for the case of reptation. And for all the cases, the respective equations have been discussed during the course, so those need to be applied, and then the whatever quantity is being asked for, that can be calculated. So I that basically reviews the part of this course that was covered after the first live session. So if there are any questions, you can type in the box and I'll try to answer. I see there's a question regarding exam registration. So there's a question that the question is that I could not register for the exam before due date. Now when will I get chance to register for the exam? So exam registration for these NPTEL courses is not something that is uh, decided or under the control of the instructor of the course. So for registration related matters, you'll have to contact the uh, NPTEL office, probably the head office in IIT Madras. Uh, because if the deadline has passed, then there's I mean, from the side of the instructor, from my side, there's nothing I can do to allow exam registration. This has to be taken up with the central NPTEL office, and whatever information they have, that they can provide you to clarify your doubt. So if there any questions, any other questions, any questions in general you can ask regarding the course or the assignments. The assignments, the solution for the assignments, I'll try to post this all solution to all the assignments on the portal maybe within 1 week. So you have your exams in the second half of December. So by the end of November, the solution to all the assignment problems will also be posted, so that so if you were not able to solve a few problems and you were not clear about what the steps are for solving them, then that should become clear from that. So it appears that there are no questions at the moment. Remember that if you have questions, any questions that come to your mind later on, you can always post it on the portal, and I'll try to answer those questions. So since at this moment there are no further questions from your side, so I'll like to conclude this live session. Okay, I think I have received a couple of questions just now, so maybe I'll just address those and then conclude. So one question is, will exam pattern be same as assignments? So the questions that you got in the assignments, in the exam also, the type of questions will be similar in the sense that either you'll get multiple choice questions which will have only one correct answer, or the questions will be where you'll have to will be short answer questions. You'll have to type in your answer, which will be a numerical value. So for short answer questions, the required decimal precision that is needed, that will be specified, as well as the units in which you have to write your answer, that also will be specified in the question itself. So it will be similar to what you got in your assignment questions in that sense. The specific questions itself, of course, will be different, but the type of questions, as well as I mean, in the assignments, I tried to cover uh, the the different parts for every week, the different topics that were discussed during the week. I tried to include as much as possible at least one problem on the different topics that were discussed. So in the exam, of course, you should, all the assignment problems that you've got, you should be comfortable with those, because they will of course come in handy while preparing for your exam. And pattern wise, other details about the exam I think should be available on the website. There will be questions which will carry 1 mark, some may carry 2 or 3 marks also. Uh, uh, there can be many standalone questions, and there can also be questions which will be based on some common information. So you can have some information about a problem, and then 2 or 3 questions based on that information. So similar questions have appeared in your assignments also. So I'd urge all of you to make sure that you are fully comfortable with all the assignment problems. So while preparing for the exam, of course, you have to go through all the lectures, and whatever slides have been uploaded, go through those and make sure that you know all the relevant formula and concepts. In addition, all the assignment problems, how they are solved, you should familiarize yourself with that also. So in that sense, it's important that you know how to solve each and every assignment problem. Even if you could not solve it while submitting an assignment, I'll upload the solutions now. You go through them, try to understand, and if there are any questions on the solutions as well, you can still post those on the portal, and I'll try to answer. So that was one question. There was just one more question again. What will be the question paper pattern? It's similar to the previous question. So the type of questions will be similar to what you got in the assignments. The specific questions, of course, will be different. So you can have multiple choice, short answer questions, multiple questions based on common information. So all those things will be there. Okay. So I think both questions are similar, and I've already addressed these concerns. So And in the examination, an attempt will be made to have questions from each and every lecture. So all the lectures in the different weeks that we have had, uh, I mean, as much as possible, it will be attempted to have representation from all those lectures in terms of the questions that you'll get. So any other questions about the course or even the exam? I have another comment. It just says internal marks with a question mark. So can you elaborate what you want to ask? Internal marks, it's not clear what you mean by that. Assignments, of course, carry some weight. So all the assignments that you have submitted, based on that, their weightage will be considered, as well as the what you get in the final exam, and together the whatever you get finally in this course, the score that you get, that will be a combination of your assignment score and the final exam score. So all this is mentioned on the front page of this course, so you can look that up. Yeah, so as I said, assignment marks, of course, they will form part of the final score that you get in this course. All the assignments that you have submitted, their marks together will be considered. They will be that will be assigned some weightage, and remaining will be for the final exam. Final exam will carry definitely more weightage than the assignments together. And as I said, if you just visit the home page of this course, the details about what will carry how much weight, that those things are mentioned there. Okay, so you can get a better idea of these things there. Any other questions? Yeah, so now since there are no more questions, now I'll conclude this live session. And as I said, if you want to have any other queries answered, then you can always post on the portal. I'll be happy to answer the questions there. So that brings us to the end of this live session, and I wish you the best of luck for your examinations. Thank you.